Bismillah. Bismillah Rahman Rahim. So let's discuss the remaining portion of basic excitation. That is the second question. That is how much force would be transmitted to the mass from the base excitation. So here you see the Freebird diagram of the system. So this is the mass, and this is the spring force because of the motion of the base and the mass kx minus y, and this is the damping force. At this instance, the mass is moving in the upward direction, and we have assumed that x is greater than y. So we have the free body diagram, and as we discussed that here we have the base, and the base and mass is connected through spring and damper. So these two forces are transmitted from the base into the mass. So to the mass, the spring force is transmitting, and also the damping force is transmitting. So the total force that is transmitted to the mass is actually equal to F. Let's say it's F, so it would be the spring force, which is K x minus y, plus the damping force, which is C times x dot minus y dot. And from the dynamic equation, that is equation of motion of the system, the equation of motion was mx double dot plus kx minus y plus c times x dot minus y dot. And rearranging the equation of motion, we could also write down the equation of motion as k times x minus y plus c times x dot minus y dot, and it must be equal to minus mx double dot, because mx double dot is equal to minus spring force minus damping force, and bringing the these two forces on this side of the equation, whereas the inertia force on the other side of the equation, we would have a minus sign here. So we could also say that the transmitted force, the force which is transmitted to the mass, is actually equal to minus mx double dot. So if we have the mass of the system and the acceleration at which the mass is actually moving, then we could also use this equation. So the force transmitted could be found out using this equation and also using this equation. Let's say that if the steady state response, time response, is x sine omega t minus phi, then if we take, if we differentiate this twice with respect to time, then we would get the acceleration at which this mass is vibrating or moving. So x double dot of time is equal to minus omega square x sine omega t minus phi. So plugging this here in this equation, so we have minus sign here and minus sign here, so it would become plus, and we have m mass, so this mass is here, and remaining is actually x double dot. So the transmitted force in terms of mass is equal to m omega square capital X sine omega t minus phi. So this is actually the transmitted force in terms of mass, and here we have the transmitted force in terms of stiffness and damping. We could use both equation. So we got the model for the transmitted force in terms of mass. So if we look here, so this is the sinusoidal function, this is the sine function, and this is the coefficient of the sine function, and the coefficient of the sine function is not other than, what is this? This is actually the amplitude. This is the amplitude of the transmitted force. So we could write down this as f of t is equal to f subscript t sine omega t minus phi, and ft, this is actually the amplitude of the transmitted force, and it is actually equal to m omega square x. So Ft is the magnitude of the transmitted force due to base excitation. So from this equation, we could take out x. So x is equal to, you have to divide this equation on both sides by m omega square, or bringing this quantity on the other side of the equation, capital X would be equal to Ft m omega square. And what other thing we are doing here, I'm multiplying the numerator by k and dividing by k. M by k is 1 over omega n square. So afterward we would have ft by k omega by omega n whole square. So which omega by omega n, we define this as a frequency ratio r. So capital X would be equal to ft k r square. In the last lecture, we come up with the mathematical model or analytical model for the displacement transmissibility, which is capital X by Y. And this is actually the model in terms of stiffness, damping, and mass. And this is the actually the same equation in terms of damping ratio and frequency ratio. So what we have to do, we have to put for this X, because we want to find out equation or mathematical model for the transmitted force. So we have this X in terms of Ft. So we have to put for capital X, that is the amplitude of the steady state response, in this equation, and then we would see what we get. So we have the transmitted force in terms of mass, and we have deduced that equation in terms of, we have deduced the equation for the amplitude of the steady state response in terms of the transmitted force and frequency ratio, and we are plugging that in the displacement transmissibility. And after putting for X, which is Ft, K, Y is from the other equation, and bringing this R square on the other side of the equation, because here we have R. So we have Ft by K Y is equal to R square under the root 1 plus 2 zeta whole square by 1 minus R square plus 2 zeta r square. So if you look at this side of the equation, it is all values are ratios, damping ratio and frequency ratios. So it is dimensionless. Similarly here, this is the force. The unit is Newton, and also stiffness times displacement. The unit is Newton. So actually, we have a completely dimensionless equation. This side is actually known as the force transmissibility, that how much force is actually transmitted to the mass when it is subjected to the base excitation. So we have now actually the mathematical model in terms of zeta, and in terms of damping ratio, and in terms of frequency ratio. This is somehow the frequency response. This is actually the frequency response of the system. So now we have to simulate the mathematical model that we have developed for the force transmissibility. So we are taking the force transmissibility along the vertical axis, which is Ft Ky, and the independent variable is the frequency ratio. So we are taking that along the horizontal axis. So simulating that equation for frequency ratio from 0 to 4, and plotting for different values of damping ratios. So this is the simulation of that equation. So we could divide the plot into two regions based on the resonance or frequency ratios. When the frequency ratio is 1, so we have this portion of the plot. When frequency ratio is more than 1, we have this portion of the plot. So we could see here that when the frequency ratio is less than 1, so at lower frequency ratios, the force transmissibility would be less. It would be less. And at very low frequency ratios, it would be very near to 0. However, as we increase the frequency ratio or frequency of excitation, and as we comes near to the resonance, then maximum amount of force would be transmitted to the base, to the mass m. But however, it depends upon what? It depends upon the value of zeta, damping ratio. And smaller the damping ratio, more would be the force transmitted. So meaning that if we want that less amount of force is transmitted at the resonance. So for that you have to increase damping in the system. In other words, we could say that, or we could conclude that, if the damping in the system would reduce the amplitude of the transmitted force at the resonance. If you want that at resonance less amount of force need to be transmitted to the mass from the base, then we have to increase damping in the system. And also there is one more point for the discussion, which is at the frequency ratio of under root 2. You could see here all lines are passing through after the resonance. All lines are passing through this point, and at this point the force transmissibility is 2. It is 2. However, if we further increase the frequency ratio, then you see that actually for some damping ratios the force transmissibility decreases, and it would again start increasing. And here you see that for these, when the damping ratio is less, you could see that the force transmissibility would further increase as we increase the frequency ratio. What is actually the reason behind that? So if we go back and we look at this mathematical model, here what we see r square, the square of the frequency ratio. So from this, we could easily interpret that when the frequency ratio is less and you take the square of that, it would become more or less. But when the frequency ratio is more, if you take the square of that, that amount would exaggerate. And this is actually happening here. And this is happening for the damping ratios. For less damping ratios, it is happening after a frequency ratio of under 2. However, for the high damping ratios, uh, for less damping ratios, uh, for less damping ratios, you could see here that after a frequency ratio of almost 2.2, afterward the force transmissibility would increase. It would increase. However, for undamped system, where zeta is equal to 0, you could see that if the frequency ratio is further increased, the force transmissibility would be always 1 at higher frequency ratios. However, if we look here for higher damping ratios, here at higher damping ratios, after under root 2 frequency ratios, the force transmissibility would increase, and it is almost linear for a critical damped system. It is almost linear for a critical damped system. However, it then increases exponentially for the other damping systems where the damping ratio is less than 1. The next question that one could ask, that how much relative motion is transmitted to the mass m, because here the base is moving and also the mass is moving, and this end of the damper is moving and this end of the damper is moving, also this end and this end of the springs, they are moving. So mass is subjected to the relative displacement, and also the springs and dampers are subjected to the relative displacement. So, relative displacement here is, let's say, z, and let's assume again x is greater than y, so z would be equal to x minus y. So x is an absolute displacement. This is absolute displacement of mass. Y is the absolute displacement of the base. However, z is the relative displacement between the mass and the base. So let's say z is equal to x minus y. So using the this is the um, free body diagram for our system, which we have discussed previously or last time, and using the Newton's second law of motion on this free body diagram. summation of all of the forces which are actually along the displacement x is equal to m x double dot, that is mass times acceleration. Here we have a spring force which is opposite to the displacement, so minus k z minus damping force c z dot in this case, because z is equal to x minus y, so z dot would be equal to x dot minus y dot. So we would have minus c z dot, and it must be equal to m x double dot. X double dot we could find out from this equation. Z double dot is equal to x double dot minus y double dot, and from that equation x double dot is equal to z plus y double dot. So after rearranging the equation, we would have m z double dot plus c dot plus kz is equal to minus m y double dot. So we have the equation of motion in terms of relative displacement z. Again, let's the base excitation y is equal to y sine omega t. It is periodic and sinusoidal. So in that case, here we have to plug for y double dot. So differentiating this once, we would get the velocity at which the base is moving, and differentiating this twice, we would get the acceleration at which this base is moving. And y double dot would be equal to minus minus omega square y sine omega t, and plugging that here in this equation of motion. So the equation of motion would become m z double dot plus cz dot plus kz is equal to the minus with y double dot, and this minus would become plus, and we would have m, this m, and then omega square y sine omega t. So we got the equation of motion in terms of relative displacement z. Next, if we look at the equation, again we have a second order differential equation, which is non-homogeneous differential equation here, because here again we have a function of time. This is not zero, so non-homogeneous differential equation. And we have already discussed the solution of such equations, which we actually did in case of the 1 degree of freedom system, which is subjected to force excitation. And the equation of motion that time would be m x double dot plus c dot plus kx is equal to f naught sine omega t. So by simply by comparison, we could get the solution. So there is no need of doing the derivation again for the response of this equation. The response of this equation would be z of t. Z of t. So here, if we have, this is the equation of motion. For this equation of motion, we have this response, steady state response, x steady state of time is equal to capital X sine omega t minus phi. And the mathematical model for the amplitude of the response, capital X is equal to f naught divided by under the root k minus m omega square whole square plus c omega whole square. And the initial phase phi is tan inverse c omega divided by k minus m omega square. So we have already derived these for a single degree of freedom system which is subjected to force excitation. Here by comparison, what we have, if we compare here, so instead of this f naught, we have m omega square y. So simply we could say that this is actually the amplitude. F naught here is equal to m omega square y. In other words, here in this mathematical model, we have to replace f naught by m omega square y. And here the steady state response in terms of relative displacement z steady state of time, we could write down this as capital Z, which is the amplitude of the relative displacement sine omega t minus phi. Here we have to replace this x, capital X, by capital Z, and this is not by m omega square y. So instead of x, we have capital Z instead of f naught m omega square y. Phi, phi would remain the same equation, c omega k minus m omega square. So just by comparison and similarity, we could very easily determine uh, the steady state response in terms of the relative displacement, and we could have a model for the amplitude of the relative displacement and initial phase of the relative displacement in case of base excitation. So now we have the relative displacement steady state response z sine omega t minus phi 1, or phi 1, which is actually equal to tan inverse 2 r 1 minus r square. We have already developed those equations, and as so we have here, you could see that we have capital Z in terms of stiffness, mass, and damping, and the initial phase in terms of damping, stiffness, and mass. We could also deduce this equation in terms of damping ratio and frequency ratio, and we have already learned that in a number of times in previous lectures. So rewriting this equation, so in order to make this or convert this into a dimensionless equation, so we could bring this y on this side of the equation. So here we would have z by y, and we could take this k common, so it would become k square, and this is under root, so afterward it would be k. So we could also take k common here, it would become k square, it would be c by k. And here we again k square here and k square here, we could take common, and then we could bring that out of the sign of under root. So outside we would have k. Inside here we were 1, and m by k is 1 over omega n square, and c by k is 2 zeta by omega n. So we would be repeating the same procedure, and this k we could write down with the m, so we would have m by k, and m by k is actually 1 over omega n square. So after doing that, bringing the y here, and then taking k common here, and it would become k square, bringing that out of the under root, and doing all that mathematical uh, simplification, then afterward we would have r square. R square is omega square by omega n square, 1 minus r square whole square plus 2 zeta r whole square under the root. So here we could see relative displacement. This is the amplitude of the relative displacement, and this is the amplitude of the base excitation. So here on both sides we have numerator and denominator, we have displacement. So again, this is a displacement transmissibility, but now in terms of the relative displacement. And here we could see ratio, frequency ratio, and damping ratio. So we have a completely dimensionless equation. Similarly, we could rewrite this equation in terms of frequency ratio and damping ratio. Simply here we have to take k common, so this would become 1 m by k. M by k is 1 over omega n square, and k we could write this k here with c, so c by k is 2 zeta by omega n. So simply by doing that, phi would be equal to tan inverse 2 zeta r by 1 minus r square. So we would have the initial phase in terms of the damping ratio and frequency ratio. So very simply, by actually rearranging the equation of motion and then comparing with the equation and solution of the amplitude of the response in case of force vibration, we could deduce the mathematical model for the displacement transmissibility and the initial phase for the base excitation in terms of the relative displacement. Now here you could see the simulation. So we have the model. So now we are simulating that mathematical model in order to judge the behavior of the system based on the model, because if you are not simulating, so it would be not possible to actually conclude some important information which are actually hidden in the mathematical model. So simulating that, here along the vertical axis we are taking the displacement or transmissibility in terms of relative displacement, and along the horizontal axis we are taking the frequency ratio, and the simulation is done for a frequency ratio from 0 to 4 for several values of damping ratio. Here the damping ratio is 0, damping ratio 0.1, 0.15, 0.25, 0.5, and this is the damping ratio is equal to 1. So again we could actually divide our simulation plot into a number of areas. Here we could see that in this area actually the frequency ratio is actually less than 1, and in this area the frequency ratio is actually more than 1. The frequency ratio 1 represents the resonance, meaning that when the frequency ratio is less, if it is too less, then the displacement transmissibility in terms of relative displacement, that would be very small, even negligible. But as we increase the frequency ratio, then depending upon the damping ratio, the displacement transmissibility would exaggerate, and it would be optimum, it would be maximum near the frequency ratio of 1 or near the resonance. When the damping ratio is less, then the displacement transmissibility would be worst. It would be worse. It would be more, which we don't want. So if you, in order to want, you decrease, you want to decrease the displacement transmissibility to the mass, so we have to increase what? We have to increase the damping in the system. At higher frequency ratios, you could see that all these simulations are converging. They are converging at one. So what does that mean? That irrespective of the damping ratios, at higher frequencies ratios, the displacement transmissibility would be almost 1. It means that z by y is equal to 1, which means that z would be equal to y. Z is equal to y means that at very high frequency ratios, the relative motion of the mass would be approximately equal to the amplitude of the base excitation. So very important information. So at high frequencies ratios, very little amount or equal amount would be transmitted to the mass in terms of relative displacement, and the amount which is transmitted, it would be actually equal, approximately equal to the amplitude of the base excitation. However, near the resonance, z would be too much more than capital Y. The displacement transmissibility would be high.